Hi class, welcome back to the continuation on the lectures on electrodynamics, and this is the second part of chapter 5. Again, our main reference is Introduction to Electrodynamics by David J. Griffiths, and I recommend that you get a hold of a copy of this book. So we will start with example number 5.3, which we have actually accidentally stopped last session. So here, a rectangular loop of wire supporting a mass M hangs vertically with one end in a uniform magnetic field B, which points into the page in the shaded region 5.10. So when you say points into the page, the direction of that is if this is your y-axis, this is your x-axis, then what points out of the page is this direction, which is z, and this is going towards you, and then the x is the negative z axis. So into the page would be this one. So for what current I in the loop with the magnetic force upward with for what current I in the loop with the magnetic force upward exactly balance the gravitational force downward? So let's look at the solution. So in this case, the current must circulate clockwise in order for I cross B in the horizontal segment to point upward. So the force is equal to IB times A, where A here is the width of the loop. So here your magnetic field is going, in this direction, going into the page, and your current must be here, going clockwise in direction. So this is your I, this is your B. So using your right hand, I cross B. So this is like, if you look at it, B would be like this and your I would be here. And so if you cross them using your right hand, I cross B, it gives you this force. So if you have this, then your force would be in this direction, going upward. So you have a magnetic field that's perpendicular to the current. So this one here, IB sine theta, but theta here is 90 degrees, so this is just IB. So you have your force as IB times A. So again, let's look at the definition of force. If we, here, the L here, the DL here would just be a straight line, so the integral of that would just be the length of the horizontal part of the loop, which is just A in this case. Here you just have A there. So finally, our magnitude of the force is going up, IBA, and of course you don't have to include the the lower segment, because the lower segment will neutralize this force, this one. If you put the whole loop here, this will neutralize this one. And also this one does not contribute because these are perpendicular to um, the resulting force there um, would cancel each other on this part. You see your right hand rule. So anyway, so to balance the weight, which is equal to mg, we must therefore equate IVA to mg and get the current here. So now, what happens if we now increase the current? What happens then? Then the upward magnetic force exceeds the downward magnetic force of gravity, and the loop therefore rises, lifting the weight. So here you would you would um, you would think that magnetic force is doing the work, but no, it the magnetic force does not do work at all, because it's always perpendicular to the direction of the displacement. So it doesn't work. That what does the work here is when you increase the current, it's because of the work done by the battery. So um, it's really the work done by the battery that you're um, talking about. It's not of the magnetic force. And the work done by the battery is equal to this, but equal to this here, but it's not work done by the magnetic force, because as I've always said, magnetic force is perpendicular to the displacement. So anyway, that's the work done by the battery. So let me just show you for your readings here. So this is it. When charge flows over a surface, we describe it by the surface current density K, defined by this one here. So if you get a strip on that surface, you will have like a wire. So if consider a ribbon of infinitesimal with DL perpendicular running parallel to the flow, you have here is just like a wire. So the surface, the whole surface here is just uh, like wires putting side by side uh, onto each other, besides each other, and so they form a sheet. If the current in the ribbon is dl, the surface current density therefore is this one here. So K is the current per unit width perpendicular to the flow. In particular, if the mobile surface charge density is A and its velocity is V, then your K would be here, this one. So in general, K will vary from point to point over the surface, reflecting variation in and in sigma. This is supposed to be sigma here. So the magnetic force on the surface current would be this one. So you can check out the details in the calculation. Here's a caveat here. Just as E suffers a discontinuity at the surface charge, so B is also discontinuous at the surface current. When the flow of charge is now distributed throughout the three-dimensional direction, we describe it by volume current density J. By the way, this is supposed to be a vector, so you have to write this as this one like that. So we describe it by the volume current density J, defined as you can see in the figure, defined by this one here. So it's now volume current density. So consider a tube of infinitesimal cross-section dA running parallel to the flow. Here, one there. So the current volume current density would be this one. In other words, J is the current per unit area perpendicular to the flow. If the mobile volume charge density is rho, here is rho, and the velocity is v, then your current density would be, or current per unit area would be rho times v. So our magnetic force on a volume current therefore is equal to this. So you have to be careful in solving problems. When you have a sheet, then you will just have to use this formula, this one. And if you are dealing with current flowing in a volume, then it would be this one. But for a wire, it will only just be F is equal to integral of I cross B times dA. Times, no, sorry, I'm very sorry for that. Times dL. So it will just be that. So anyway, let's now go to example number 4. So a current I is uniformly distributed over a wire of circular cross section with radius A. Find the volume current density J here. So of course you have current I flowing in this direction, and then your area perpendicular to the flow is, or to flow, is pi a squared. So you will have your current density to be just I over pi a squared. So now suppose the current density J in the wire is proportional to the distance from the axis. This means that as you go away from the axis, and if K is like a positive constant, then it would increase. So J would be of course given by that. So find the total current in the wire. So because J varies with S, then we must integrate 5.25, which is this one. So now the current in the shaded patch here, this one here, is of course equal to J dA, perpendicular, but the dA in this case is also SDSD phi. So when you do the integration, you will have this one. This is your J, and this is your dA. So you will have 2 pi k integral of S squared from 0 to A, and so your current is equal to 2 pi k A cubed over 3. So according to equation 5.25, the current crossing the surface S can be written as this one, integral of J dot dA. That's why you have perpendicular area with the current flow. But this is also, this one is also equal to this when we review our lectures in chapter 1, in the first chapter. I mean, you can also write this expression as this one. So because charge is conserved, whatever flows through the surface must come at the expense of that remaining inside. This means that if you're putting charge on one side, so if you have a tube, if you're putting something on one side, what comes out is the same thing as the other side, the same amount. But of course they may not have the same speed, but the amount is the same. So we have here this equation, and of course if you do comparison, this one is this can be compared. So you will have your divergence of J would be equal to just the time derivative, partial derivative of the density, current density. I'm sorry, charge density, rho. By the way, this is now called the continuity equation. This one. For translating equations into forms appropriate to point, line, surface, and volume currents, you may use the substitution in the equations. This correspondence, which is analogous to this one, this is supposed to be rho, not P, for the various charge distribution, generates 5.15 in the, well, you can review the lecture from the original Lorentz force law. Now we'll go to the Biot-Savart law. So this is the Biot-Savart law, and we'll start with the steady current. Stationary charges produces electric field that are constant in time, hence the term electrostatics. And steady currents are produced by, steady currents produce magnetic fields that are constant in time also, and the theory of steady currents is called magnetostatics. So they produce um, magnetic fields that are constant in time. So for stationary charges, you have constant electric fields, that's electrostatics, and steady currents, you have constant magnetic fields, that is magnetostatics. By steady current, uh, we mean continuous flow that has been going on forever without change, without charge piling up anywhere. And of course, there's no such thing in practice as a truly steady current, because only in situations which are ideal, but there's no ideal situations in the universe. But you can approximate any system to ideal, but you can never attain it. So when a steady current flows in a wire, its magnitude I must be the same all along the line. Otherwise, charge would be piling up somewhere, and it would not be a steady current anymore. So by the same token, this is actually here, this is rho, not P. The partial differential of with respect to time of the charge, volume charge density would be equal to 0 in that case, and hence the continuity equation would just be left with the divergence of J equal to 0. So that is for steady currents. So we will now get the magnetic field of a steady current produced by a steady current. So the magnetic field of a steady current is given by the Biot-Savart law, which is this one. It is proportional to the current. So if you have a large current, the magnetic field would also be large, and this is of course parallel. The current is always parallel to the current, so you have to have a cross here with another vector, and that's with a vector r that's perpendicular to the supposed to be perpendicular with it's the distance between the point you are going to measure the magnetic field, not necessarily perpendicular to I, but any point where you want to measure the magnetic field. So if it's perpendicular, then the sine of the angle is just equal to 1. So anyway, I flows in the wire. In this case, you have just a wire. That's I. You can get out the magnitude of I because you have a steady current. I is supposed to be constant. So here you have dl. Now it's what is left in this vector here, I. So dl will just have the same direction as I, or you can say dl prime, and then you cross it with r, and this is of course the distance between the point and the wire. So the integration is along the current path in the direction of the flow. dl is an element of the length of the wire, and r is as always is the vector from the source to the point r. And of course here you have the permeability of free space, which is one of the proportionality constants aside from the pi. This is just equal to nu sub O equals 4 pi times 10 to the negative 7 newtons per ampere square. And we look at it in the figure below here. So this is any point, and then you have dl here, and then you have r. So these units are such that B itself comes out in newtons per ampere meter as required by the Lorentz force law. So you can also have the unit as in Tesla, which is just equal to 1 Newton per ampere meter. So Biot-Savart law plays a role that is analogous to Coulomb's law, and as you can see, there is also a dependence on 1 over r squared. So the distance, when you go far away from the source, or from the current source of the magnetic field, you will feel very weak magnetic field far away. But if you go near the current, you would feel a greater magnetic field. So example 5.5, find the magnetic field a distance s from a long straight wire carrying a steady current I. So you have here current I, and then you're measuring the magnetic field here. So by using the right hand, your right hand, you have you put your thumb in the direction the direction of the current, and then your magnetic field would have to be in the direction that is pointing towards yourself. So that's why it's a dot here. It's a dot. The direction of the magnetic field into the page would be this one. So in this case, you have dl sine alpha, dl sine alpha, which is the alpha is here. So this is pi minus alpha, so that your sine alpha would be the same as cosine theta here. So your L prime would be S tangent theta, and then your DL would be this. So our S now would be equal to this, and our 1 over r square would be given by that. So this is now this is the distance between the current source and the point, and we saw that S is just equal to this one. And now we substitute that to the Biot-Savart law, and then we get this one. So for a segment, a wire segment, this is the magnetic field produced by this segment here. So how about when the wire is very long? What happens when the wire is very long? Then what happens to your theta? Theta 2 approaches to 90, and theta 1 approaches to 90. So what is sine 90 and sine 90? Theta 1 would approach to negative 90, I mean. So what happens? Your magnetic field becomes this. So it's just the direction would be for this particular point. For this particular point would be going towards you. But at this point, for example, if you're choosing a point here, then the magnetic field would be in this direction, because you have to use your right hand, and below the point below would give a direction that's going into the page. The upper point would have to have a direction of towards out of the page. So now, as an application, we will find the force between two long parallel wires, distance d apart, and carrying currents I1 and I2, this figure. And the field at what is the field due to the wire 2 on to wire 1? So of course we have calculated that, and this is just the field there. So if you use your right hand, you curl the wire I2, and so you will be giving us a B in this direction here, which is of course this one. So that's the force there. So the force, if you try to cross I1 using your right hand to B, then it will give you a force. It will give you a force in this direction. So it is attracting, I2 is attracting I1 in that case. So if you have parallel wire with the same direction of current, then both wires will attract. If you have opposite direction, then they will repel, because if I2 would be in the opposite direction, the force would be in this direction. So that's the, and so of course the force between two wires would have to be given by this, using the Lorentz force law back in the lecture, first part of these lectures. So of course if you have a length that is infinite, it would be practical to use force per unit length, and the force per unit length would just be equal to this. Okay, and now let's go to example 5.6. Now find the magnetic field held out. The field a distance z above the center of a circular loop. This is field actually of radius r, which carries a steady current I. So here you have two loops, but the loops have different radius, and you're going to find a magnetic field a distance z above the center of a circular loop of radius r here. So the magnetic field there, if you use your right hand, so you have I cross r, this is your current I. If you get this point, your current would be in this direction and your R would be in this direction, so they're perpendicular to each other, and so if you cross them, so you will have a B in this direction. So that's this is now the B, the dB, I mean, because you're dealing with a infinitesimal part of the wire. So of course the field dB attributable to the segment DL DL points as shown. As we integrate DL around the loop, DB sweeps out a cone. The horizontal components cancel, of course. So you have, if your DB is like this, you will have an opposite DB, and the horizontal components will cancel, so your total magnetic field will just be in that direction. So you, of course, you're at the center, but if you're not at the center, then DB would not be pointing in this direction. So the horizontal components cancel and the vertical components combine to give your DB this one here, that form. So in this case, cosine theta and r square are constants, and so integral of dl prime is simply the circumference of the circle, the circumference of the loop carrying the current I. So it's just 2 pi r. So in this case, your magnetic field will just have this form. So by the way, for surface and volume currents, the Biot-Savart law becomes this one. So it's easier to calculate currents in wires, but of course you have the formula for surface currents and volume currents. By the way, I would just like to point out that you might be wondering why we cannot use this one, because well, as discussed, a point charge does not constitute a steady current, and the Biot-Savart law, which only holds for steady current, does not correctly determine its field. So you need to have a steady current. You have to have charges, continuous charges that's moving, before you can produce magnetic field, not by a single charge that's moving. You have a continuous charge distribution that's moving. So you have to take note of that. This is not correct. Although a charge can be affected by a magnetic field, which is of course produced by a current, may not be a steady current. So a charge is produced by a magnetic field. A charge is affected by a magnetic field, and the magnetic field is produced by a steady current, not by a single charge. So that's it for today's lecture, and the next time we will be discussing continuation of this magnetic field, and we will be looking at the divergence and the curl of the magnetic field. Of course, the divergence of magnetic field is 0, but the curl will not be 0, because it curls in a source, as you can see in the figure 5.27. Or maybe we could discuss it now. The magnetic field of an infinite straight wire is shown in 5.27. The current is coming out of the page. So if you look at this, you will see that it has non-zero curl. Unlike electric field, when you see a charge, the magnetic field is going out of the charge. If you have a positive charge, so it's diverging from the source. So you have a divergence of the electric field. So divergence of E is not equal to 0. But the curl of E is of course equal to 0 because it does not curl in the source. But for B, the divergence of B is equal to 0. But the curl of course is not equal to 0. So according to equation 5.36, the magnetic field around a wire with current I. So if you're looking at the magnetic field a distance s away from the wire, that would just be equal to this one. And yeah, if the wire is at the center of the circle. But notice that the answer is independent of S. That is because B decreases at the same rate as the circumference increases. In fact, it does not have to be a circle. Any old loop that encloses the wire would give the same answer. For if we use cylindrical coordinate system with a current flowing along the Z, then your magnetic field would just be given by this direction, phi hat. So in this case, your DL is given by this coordinates. So your B.dl would be this one. And by the way, this assumes that the loop encircles the wire exactly once. If it went around twice, for example, the phi would run from 0 to 4 pi. And if it did not enclose the wire at all, then phi would just go from phi 1 to phi 2 and back again. But the integral of d phi there would just be equal to 0. So the loop should encircle the wire at least once. Now suppose we have a bundle of straight wires. Each wire that passes through our loop contributes, therefore, this one here. It's like Gauss law. When you have a Gaussian surface and it encloses a charge, when you enclose more charge, then the electric field that is produced on the surface of the Gaussian surface, surface, then would also be proportional with the enclosed charge. So if it's the bigger the charge, the bigger the electric field, the lesser the charge, the lesser the electric field. But in this case, also for magnetic field, when you enclose more wires, then you will be given more magnetic field in the surrounding of the wires. So this is the line integral, then would have to be this one here. So it depends now on the enclosed current, where I enc here, or I enclose, is the total current enclosed by the integration path. And of course the integration uh, this integration gives you this one. This just looks like the Gauss law. B dot D sorry E dot dA. In this case you have a dA because you're using a Gaussian surface, say a spherical surface or a cube or any symmetric surface. So this is mu sub OI enclosed, and that your for your magnetic field it would be this. In your magnetic field it's not dA but it's dL. In that case you're just enclosing the wires or the bundle of electric currents by a loop. Now I enclosed is also equal to this integral of J dot dA. But if you apply Stokes' theorem here, if you apply Stokes' theorem there, that would give you this one, and that you'd be able to get the relationship by comparing the two equation. You compare, not really cancel but just compare. You can see that here is your curl of B. So the curl of B is not equal to 0 because as you can see the magnetic field really curls on the wire. So yes, this is the correct result, but the derivation is flawed, but well, of course this is the correct result. Well, we can discuss more on that in the next section. So formally, the Biot-Savart law for the general case of a volume current, you have this for a volume current. Of course, this is just I R prime cross R if you have just a wire. So this formula gives the magnetic field at point R, X, Y, Z in terms of an integral over the current distribution J, a function of X prime, Y prime, and Z prime. So B is a function of X, Y, Z, and J is a function of X prime, Y prime, and Z prime. The integration is over the prime coordinates, so the divergence and the curl, this one curl, are to be taken with respect to the unprimed coordinates. Applying the divergence to the equation 5.45, we obtained this. And of course, invoking the product rule number 6, this is rule, so we will have this one here. But of course, the curl of J is equal to 0 because J does not depend on the unprimed variables. So this is 0, so therefore and of course the divergence of B is equal to 0, since you also have this to be 0. So the divergence of the magnetic field is always 0. So, okay. So we have the first result, the divergence of magnetic field is 0. So applying the curl to B, so we have this. Again, expand the integrand using the appropriate product rule. In this case, you have, if you could remember, rule number 8. So your expansion would be this one here, and so that you can put them back into the integral. By the way, this one integrates to 0 if you put this one, these things here. If you, the whole thing, if you put back here, that will integrate to 0. In the first term involves the divergence, which we encountered before in chapter 1. It involves this kind of factor, and you can actually change this with this, and so you have to just put there. The second term already integrates to 0. So so this is the integral of this is when your function jr is a function of r by virtue of the Dirac delta property. So therefore your curl of B is not equal to 0, and it's just equal to mu j of r, the current density j. So it's not 0, so therefore, yeah, our using your right hand rule, of course, the magnetic field curls the current I, or the current curls the current source, I mean, so it's not equal to 0. Now let's look at the second term in equation 5.50, which integrates to 0. So because the derivative acts only on the r prime, r hat, r square. By the way, this is not a vector, this is ordinary r. This is just over r square. It's not a vector. So anyway, please take note of that. So now we can switch the del to prime del with of course the minus sign, because you have here your r is just equal to r minus r prime. So we're taking the derivative here, so you have to take into consideration the minus sign here, so that your minus sign will have to appear there. And so the x component in particular is equal to this, just the x component. Of course your y component would look the same, except that the x is replaced by y, and similarly for z. Now for the steady cars, the divergence of j is 0. So now for steady cars, the divergence of j is equal to 0. So you have this. So okay, that's it. And so if you therefore you integrate it with respect to prime, then it will give you using the divergence theorem, it will give you this. By the way, the reason for switching from del to del prime was precisely to permit this integration by parts. But what region are we integrating over? Well, it is the volume that appears in the Biot-Savart law in 5.45, which is large enough to include all the currents. And you can make it bigger than that, but J is equal to 0 out there anyway, so it will add nothing to the integral. The essential point is that on the boundary, the current is 0. All currents is safely inside, and hence the surface charge integral is equal to 0 or vanishes. You can, here you're integrating just on the surface, and there's no current in the surface, so it's 0. So therefore, when you go back here, this is always 0. This one here is always 0. It's always equal to 0, as I explained earlier. So therefore, our curl of B is this one. But we will discuss more of this Ampere's law in the next part of, in the continuation of the lectures in this chapter. So that's all for now, guys. I hope you learned something today. See you in the next lecture.